I'm Roberta Longley, and I'm the chair of the Eastham Climate Action Committee. We are honored tonight to have Judd Staley as our guest this evening. One of our committee members will be introducing him properly. But first, I'd like to give you a little background of how this evening has come about. We are a town committee that was created a couple of years ago by the Select Board. And our charge is to advise the Select Board and interact with the community regarding what ways that we as a community and individually can reduce our carbon footprint, as well as how we might reduce our vulnerability as a community to the potential devastating consequences to climate change. One of the ways we've found to do this is through offering forums and programs. We did 3 last year at the library, and we have another 3 this spring. This is our second of these programs. I just wanted to plug our final program, which is on May 18th here at the library. Our presenter will be Wellfleet resident Laura Holmes, and she's going to be speaking about composting, the science behind it and how you can do it at home, and about her award-winning commercial composting company in Dorchester, Massachusetts. That should be a very interesting program, as we here in rural Eastham love to compost, right? Just in case you've not been to the library before, if you need the restrooms, they're just around the corner. Also, I'll ask you to mute your cell phones while you're here in the room. And if you have not yet signed our email list, we would love to have your email address if you'd like to hear more from us in the future about future programs or other climate-related issues in the community. Now I'm going to call up Tom Ellis, one of our committee members, who's going to introduce Judd, his friend and colleague from days at working at NOAA together. Just also want to mention, that I think most of you have been offered index cards. If you find you have a question for Judd, we're going to be collecting them later on in the presentation, and then hopefully we'll be able to get to some of your questions at the end. All right, so I hope that you will help me welcome Tom McNellis to the podium.
Thanks, Roberta. Although I'm not the one to be welcoming Ian, to be welcomed, I'm thrilled to welcome Judd Staley tonight. We've known each other for at least 10 years now, I think. And I wasn't at NOAA, but I was working and supporting NOAA at the time. Judd was in the Federal Coordinator for Meteorology Office, which coordinates and focuses all of the resources and agencies in the federal government who are interested in and researching and dealing with meteorology. And as part of that, there was a lot of interaction with the climatology side, and we happened to be working on faster detection of hazardous weather at the time. But Judd brings a plethora of background to this, and I have a couple of things to give you as part of his background. He grew up in Central Ohio. He got his degree in civil engineering from Ohio State University. He was commissioned in the Air Force and went to University of Texas for meteorology. His many assignments in the Air Force over about 30 years, I think it was, included commanding 3 different weather units, science officer in Air Force base in Anchorage, Alaska, the commander of the Air Force's Climatology Center at Scott Air Force Base. He led advances in digitizing and visualizing climatological information. And during his 30 years, he's earned numerous awards, service medals, and upon retirement, he was awarded the Legion of Merit for exceptionally meritorious conduct in the performance of outstanding services and achievements. So very exciting. After retirement, he worked as a senior program manager, supporting NASA at Goddard and Langley centers. He finished up his career at NOAA as the chief scientist in that office I was mentioning, the Office of Federal Coordinator. He's a member of the American Meteorological Society, the National Weather Association, and the American Geophysical Union. And by the way, he just ran his 10th, I think, Boston Marathon just this past Monday. So please welcome Judge Staley.
I get a kick out of the fact that everybody listens quietly as you hear 50 years of things I've done, and then you applaud when you found out I ran the Boston Marathon. And that was about as hard as those 50 years, so that all makes sense. I'm thrilled to be here. I'd like to thank this organization, and especially Tom, for making this happen. This is special for me. I do this some, but to be able to do it with a group of people who are really here because they're interested and they want to be involved, and you may say you want to learn more. I will probably learn more tonight as we move through this and get to talk later on. But I'm going to talk about a problem we're all dealing with, and I recognize that many of you know a great deal about this, so to some extent I'm going to be preaching to the choir a little bit here, but a little bit of reinforcement doesn't hurt, and I am going to provide some scientific background that you may not have seen before. So we'll see how that goes. I'm going to start by talking about the Earth's energy balance. This is the basics of why we have a problem, how it should work, and what's happening. That will lead me to a discussion of greenhouse gases, what they've been like in the past, where they come from, and what their effects are, and especially the effects. That's where we can talk about the temperature and how it's changed and so on. I want to take a little side trip to talk about 1.5 degrees Celsius. If you've paid any attention to climate change, that number gets bandied about a whole lot. 1.5 degrees as a limit, and I want to talk about where that came from. And some other information about that. Finally, we'll go back to climate change impacts. Some of those will be local, some of them will be broader for the whole world, but we will be talking about this area, and then how do we respond to this. So, starting with Earth's energy balance, I like to start talking about the energy balance by taking a very simple case to get the idea across what that means, and then we'll take the more complex case. And the simple case is we have the Earth and the sun, but what we don't have is an atmosphere. So this is a very simple thing. The Earth shines down, the sun shines down on the Earth and hits the surface of the Earth, and we talk about percentages of energy from the sun. This is to avoid talking about watts per square meter and stuff like that confuses me and everybody else. So we'll just talk about percent from the sun. All the percents we're going to talk about are this 100% coming down from the sun. Well, in this hypothetical case, let's say 10% of it hits the Earth and immediately gets reflected back out into space. We don't have to worry about that anymore. The problem is we got 90% coming in from the sun. It's got to go somewhere. It gets absorbed by the land. Now the land starts warming up, and the problem you have with that is if the land doesn't figure out how to get rid of some of that heat, at some point it's just going to keep getting hotter and hotter. So it starts warming up, and we have this law of physics that says the warmer something is, the more heat or the more energy it radiates. So as it gets warmer, it's radiating more. So it keeps warming up, and it keeps radiating more, and it keeps warming until it's radiating the same amount that it's receiving. And at that point, I can't warm up anymore because it's getting rid of energy as fast as it's getting it. So its temperature stabilizes. And that becomes an energy balance. It doesn't change. Same amount coming in and going out. Well, how exactly that happens can get complicated, but the starting point is to say that there's another law in physics that says the maximum amount of energy that's radiated is in certain wavelengths, and that wavelength is related to the temperature. So think about this. The temperature of the sun is about 10,000 degrees Fahrenheit. And so if you apply this law of physics, what it says is most of the energy coming from the sun comes in the visible part of the spectrum. Visible light. That's what's shining in out there. That's visible light. Visible light, we call it visible because that's where we see with our eyes. That's no coincidence. Our eyes evolved over millions and millions and millions of years to see in the best place where you have the most efficient eyesight. Where is that? Well, that's where you got the most energy. We call it visible, but that's just where it happens to be. So that's where it's coming in. But going out, well, the Earth is about 60 degrees Fahrenheit, give or take. So going out, we get the maximum amount of energy in the radiation in the infrared part of the spectrum. So right off the bat, we got visible coming in and infrared going out. And that causes some interesting things to happen. So now we're going to take the real Earth and look at a more complex case. In this case, now we have the sun, and it's shining in down here. We have that same 100%. But as it comes down, we have the clouds, the atmosphere, and the Earth coming into play. All of them reflect some of that radiation back out into space without any interaction at all. It just goes right back out. All of them absorb some of that radiation coming in. So what we end up with is, if you look at what's reflected, 30% is reflected back out. So 70% ends up absorbed somewhere in the Earth atmosphere system. So if we want to balance this thing, somehow we're going to have to shed that 70% along the road somewhere. About 50% is absorbed by the land. So if the land doesn't keep, we don't want it to keep heating up, we got to figure out how to shed about 50% of what's coming from the sun that's absorbed at the land back out from the land somewhere. And so that's what we're going to talk about now, is how do we balance what's happening with the land. There are three mechanisms we get heat off the land. The first one is the simplest one. The land is warm, the air's touching it up above, it transfers heat to the air, that air gets warmer and it rises through the atmosphere. Real simple. That's called conduction and convection working together. And that's this one right here. The next one here is a little more complicated. This has to do with water. When we evaporate water, it takes heat to convert those water molecules to water vapor molecules. There's heat that goes into those molecules. When we evaporate something on the Earth's surface, most of that heat comes from the Earth's surface and goes into that molecule. What does that molecule do? Well, now it's vapor. It goes up into the atmosphere. Once it gets up there, eventually it's going to condense out, either as a cloud drop or a cloud droplet or a raindrop or a snowflake or something like that. When it condenses back out, it gives that heat back. And when it gives that heat back, it goes into the atmosphere. So we're taking heat from the surface of the Earth. When we evaporate that, taking it up, and when we condense it back out, we give it back. But it goes from the surface to the atmosphere. And the final way we have here is infrared radiation. And this is what we saw in the previous one. Everything went out through infrared radiation. Well, that doesn't happen here, but we do radiate in the infrared from the Earth's surface. Now, the interesting thing is, about 1/4 of what is radiated in the infrared from the Earth's surface makes its way directly out into space. About 3/4 of it gets absorbed in the atmosphere. And now we're kind of coming to the crux of the matter, getting absorbed in the atmosphere. So what really happens here? Well, the atmosphere has already absorbed some stuff coming in. The conduction and convection and the evaporation is all putting stuff into the atmosphere too. And about 3/4 of the infrared radiation is also being absorbed in the atmosphere. The atmosphere is doing all the work here. It's 64% of the radiation into space from the Earth atmosphere system is actually going from the atmosphere, not from the surface of the Earth. 6% is this bit that makes it all the way out from the surface of the Earth. Well, if you add those two numbers up, what do you get? 70%. What did we say? We had 70% entrained over here. We had to get rid of 70%. We have an energy balance. And this is a natural state of the atmosphere. Now, why did I tell you this story? Well, I told you this because this part that takes place right here is very important. How much we absorb of the outgoing radiation is absorbed by the atmosphere. The atmosphere is made up of mostly oxygen, nitrogen, and argon. And those three chemicals, those three constituents, don't absorb infrared radiation. So most of the atmosphere isn't absorbing infrared radiation. There's something called greenhouse gases. A tiny little sliver of the percentage of what's in the atmosphere are greenhouse gases. They do all that absorbing. So, people will tell you, well, there's almost no, carbon dioxide or whatever you say in the atmosphere. How can it do that? Well, all the absorption is done by those. So we're going to talk about those greenhouse gases now. Let's start by looking at just the sources of where they come from. And these are, all of these greenhouse gases naturally occur in the atmosphere, and naturally, through normal processes, natural processes go into the atmosphere and come back out. And if we leave it alone, they're balanced. There's a natural balance. What we're looking at here is the part that goes beyond the natural balance. What's happening? Well, transportation is about a quarter of the excess greenhouse gas we're putting into the atmosphere. The production of electric power is about a quarter. This is mostly what goes out to run your houses and things like that. And then industry does about a quarter. Then there's some residential and commercial, and a lot of this is things like gas furnaces, gas water heaters, your stove, that kind of thing, that are gas. And finally, agriculture is about 10%, and I always find that interesting. I think of agriculture, that's a natural thing. We're out there growing stuff, we got animals, it's all natural. Well, not exactly. We don't exactly grow things naturally these days. And so about 10% of the greenhouse gas emissions are coming from agriculture. What gases are we talking about? Well, there's three really important ones. Carbon dioxide, and this 79% is not molecules or mass in the atmosphere, it's warming effect. 79%, 80% roughly, of the warming effect of greenhouse gases comes from carbon dioxide, and that's why you hear so much talk about carbon dioxide. Methane's about 10%, nitrous oxide is a little bit less than that. We also have some fluorinated gases. We're not going to talk about that. These three naturally occur in the atmosphere and left alone naturally do their own thing coming in and out and maintain the balance. Fluorinated gases are not natural. It's something we're not going to talk about those today. So we're going to talk about each one of these individually. CO2 is the first one. I call it the big gorilla because it really is the one that's causing the most problem. 87% of CO2 in the atmosphere comes from fossil fuel use. Now, if you think of 80% of our warming effect comes from CO2 and 87% of that comes from fossil fuel use, it's not hard to connect the dots to see where the big problem is. We got 9%, about 10% is land use change, and that's kind of a funny one. It doesn't put more into the atmosphere. The land use changes have changed land use, so it's taking less out. So effectively, 9% of the increase is caused by land use changes, but it's actually because the land use is not helping us out the way it used to in terms of taking CO2 out of our atmosphere. Plants ingest CO2, and that's what the land use problem is. If you don't have lots of plants out there, there's more CO2 in the atmosphere that's not being taken out. That's the 9%. We started measuring this systematically in situ back in the 1950s on top of a mountain in Hawaii. And one of the things we discovered, this is the data from this observatory, Mauna Loa Observatory, running from when we started up until now. And one of the things we discovered, and we kind of knew this, is CO2 is distributed pretty evenly around the world, around the atmosphere. So while we're looking at Mauna Loa Observatory here, this is very consistent with what you get all the other places we measure. We measure at lots of places now. When we first started, this was the only place. We measure at lots of places. This is consistent around the world. And back when we started, we were at about 320 parts per million in the atmosphere. We are now at about 420 parts per million, 60 years later. If we take this back to the beginning of the Industrial Revolution, about 1850, about 100 years before we started, it was 280. So we went up about 40 parts per million in 100 years. In the last 60 years, we've gone up 100 parts per million. So you can see that the curve is bending upward. We're not only increasing it, we're increasing it at an increasing rate. And that's a real concern. Some people say, well, okay, so why is this a big deal? I mean, what's happened in the past? Hasn't this happened before? Things change. What's the big? Well, this goes back 800,000 years, almost 1 million years, and this is the carbon dioxide concentration we have. And we get this from a number of sources. Scientists have figured out how to go back and figure out what concentrations were in the past, and we've become very good about this the last 30 or 40 years because we've had to understand climate change. And this dotted line you see here, this is the concentration, and this dotted line you see here is at 300, and that's the highest we've had in the last million years or so. And if you take that over to the right here, you can see, remember we said when we started it was 320, so we started measuring in the 1950s, we were already above the highest level we've seen in the last million years, and now we're up here somewhere. So this is not something that just, happens to happen naturally in the atmosphere. Something important is going on here. Let's look at methane. It's our number 2 problem. This chart actually looks at both the natural and the man-made part. The natural part of methane, you can see, comes mostly from wetlands. This hatched area, these 2 hatched pieces of the pie on the right are the natural ones. Most of it comes from wetlands. That's about 40% of what's going into the atmosphere all the time now for methane. These around here that are solid are all man-made, and about 60% is man-made. So it's interesting to note that over half the methane that goes into the atmosphere is going in because of what we do and is beyond the natural state. If we were just doing the natural part, the atmosphere would process that, and it fits in very well with the energy balance. But we're overwhelming that. And interestingly enough, 60% is going to be coming from methane, is coming from human sources. And 60% of that comes from either fossil fuels or enteric fermentation and manure. Enteric fermentation is a fancy word for cow burps. And this has to do with, what we can say is 60% of what goes in methane is caused by human activity, and 60% of that comes from either fossil fuel or livestock, either through manure or cow burps. We started measuring methane systematically in 1983. So these are actual in situ measurements in the atmosphere of methane, and you can see it's gone up consistently. We measure this in parts per billion, and it's gone up consistently, and lately the rate at which it's gone up has increased, which has been causing some concern. I want to move now to nitrous oxide. It's sort of the flip side of methane. Methane, 60% we're doing, 40% nature is doing. Nitrous oxide, nature is putting 60% of the nitrous oxide into the atmosphere, and it's done through processes, either natural processes, either in the soil, in water, in the ocean, or in the air. The remainder we're doing, so we're doing the 40%. Where does that come from? Well, most of it, about 3/4 of it, comes from agriculture and soil management. And the reason for that is we use something that we refer to as artificial fertilizers. You don't think of it as artificial fertilizers. It's the stuff you put on the lawn. We spread it out in the fields to grow stuff we eat or to grow stuff that we feed the animals we eat. But that's standard. That's all nitrogen-based fertilizers is what we use. And that has resulted in a significant increase in the amount of nitrous oxide in the atmosphere. And this is a really tough one. Your question is, how do you address this without getting ourselves to the point where we don't have anything to eat? I mean, this is a really, really difficult one to work at. We can nibble around the edges by trying to be more efficient about how we use the fertilizers. But to just yank all the artificial fertilizers out is probably not going to be feasible. So we got to really work at this one. And this is, you can see that starting in 1975 through now, the increase in concentration of nitrous oxide. And again, we measure this in parts per billion. And it's really interesting. You ask the question, well, okay, CO2 is parts per million. These other two are parts per billion. Why is that such an issue? That's almost nothing. Parts per billion? Well, why is that a concern? Well, because they have different effects on the atmosphere is why that's a concern. And we look at two things when we look at effects. One of them is how long do they stay in the atmosphere? You put something in and it's gone tomorrow, it's probably not going to make a whole lot of difference. You put it in and it's still here 1,000 years from now, that's going to make a big difference because what you put in tomorrow will be 1,000 years and what you put in the next day, and so it builds up. The other thing is, how good is it at absorbing infrared radiation? they're not all the same. And so what we do is we talk about lifetime in the atmosphere and global warming potential. Well, CO2, we make the global warming potential one. It's an arbitrary number, so that's just a good baseline. We compare everything to CO2. CO2 stays in the atmosphere for hundreds of years. We don't have a good number on this one like we have on the others, and the reason is it actually stays in the atmosphere for tens of thousands of years. But the amount is very, very small when you get out to 15,000 years. It's a tiny, tiny amount. So we really don't want to think there's a lot of effect there. So as we go back, somewhere in the hundreds is where you could draw a line and say, okay, this is really not having much effect. But there's a little value judgment. So we usually say, well, that's in the hundreds of years. And we call that potential 1. But to just to give you an idea of what it means for hundreds of years, this is the Ford Model T. We sold those 100 years ago for about 20 years. 40% of the carbon dioxide that those cars put into the atmosphere is still in the atmosphere. So think for a minute about the car you're driving today and the impact it's going to have down the road. That stuff is going into the atmosphere. You can expect about 40% of it will still be there 100 years from now. Methane is about 25 times the potential global warming potential as CO2 is, and that takes into the fact that methane only stays in the atmosphere for 12 years. And even the fact that it's not in, and CO2 is in for hundreds of years, it's still 25 times as effective. Nitrous oxide stays in a little bit less, about 100 years, a little bit less than carbon dioxide, but it's 300 times as impactful in terms of it retaining heat. So what we know is that carbon dioxide, we have about 420 parts per million in the atmosphere right now, and we attribute about 80% of the warming we're getting to carbon dioxide based on 420 parts per million. If we add the methane and the nitrous oxide together, they have a grand total of 2.2 parts per million, about 1/200th of the number of molecules in the atmosphere, but they actually do 20% of the warming. So they're very effective, and there are things we have to pay attention to because of that. So what do we know about greenhouse gases? Well, they occur naturally in the atmosphere. This is not some unnatural thing going on. They're naturally balanced in human time frames. That is, if we leave them alone, they balance themselves out. However, they're increasing due to human activity, and it's those things that are causing the average global temperature to rise. So how much is the temperature rising? Let's look at the effect of this. This is a chart of a temperature rise, temperature change against a standard. So we're just looking at degrees of temperature change, not total temperature. We're starting at 1850, which is about when the Industrial Revolution started. That's hard to tie down, but about that time. And it goes up until now. And there are actually 5 lines on here from 5 organizations that do these studies to determine what the temperature of the Earth is. 2 of them from the United States. That's NOAA, National Oceanic and Atmospheric Administration. I used to work for them. They own the National Weather Service. They also own the agency that does the climatology. And they do this. Then you have NASA. You know who NASA is, Goddard Institute for Space Studies. They do one. So there's 2 in the United States. This HADCRUT here, HAD, HADS, is short for Hadley. And the Hadley Center is the climatology center in the United Kingdom. So they're contributing. And then we have the Japanese Meteorological Agency. They're doing this, and they're contributing their solution to what's going on. Those are all government agencies. About 20 years ago, a professor at Berkeley was skeptical. He was a true climate skeptic, and he was skeptical that these people were doing this right. And he wanted to make sure. So he brought together his own database of temperatures. He put his own models together, and he came up with his idea of how the Earth was warming or not warming and what was happening. You can hardly find any difference between the red line on here and this is very interesting. This is a 5013C nonprofit. It's not a government agency. It's a 5013C nonprofit. When he started out, a lot of his funding came from the Koch brothers Foundation. And these people wanted him to say, these guys got it all wrong. And it was very devastating to the climate denial community when they came out their results and they matched almost exactly what everybody else was saying. And they've continued to work on it. So we still have this 5013C nonprofit doing this work that's validating what these untrustworthy government agencies are doing. But you can see that we're seeing about more than 1 degree. If you take what's here, this is minus 2.5, and you go up here, this is about maybe 0.85, and you put those two, it's about 1.1 degree Celsius of warming since that time. And that's the number you hear. Excuse me?
What would that be Fahrenheit?
2 degrees Fahrenheit. Good question. Thank you. 2 degrees Fahrenheit. So some people ask, well, okay, we know the climate changes and temperature's going up. What's the big deal? It's done that before. And the truth is it has. But you got to really look hard to find it. This is 2,000 years. This is the year 1 here, and this is 2020 here. So this is 2,000 years, essentially since the time of Christ. And this is what we've looked back on and seen what we think the global temperatures were based on our sources for that information. And you can see what's happened here. This is the Industrial Revolution here, and during that time we actually observed it. These are reconstructed from other sources, but we actually had observations, and you can see how high this number is here compared to what we've had in the last 2,000 years. It's unprecedented over the last 2,000 years. Now I'm going to put a slide up here that's going to be a little mind-boggling, and I've got to walk through it carefully with you, but I want you to get a sense of, so you say, okay, 2,000 years, but we've been around a lot longer than 2,000 years. I mean, that's for us, that's not a big deal. So we're going to look at the big picture. This goes back 500 million years, 500,000 years, okay? And these are the temperatures. And the 0 temperature is kind of where we started at the beginning of the Industrial Revolution. It's our baseline for today, that we've got our 1.1 above. These are years down here, and the scales aren't the same, so I have to be a little careful how I do this. But we go back here. This is about 500 million years, and it goes up, this piece here goes up to about 100 million years. So it's 100 to 500 million years. And you can see if this is 0, most of the time the temperatures were pretty warm. 6 degrees higher, 5 degrees higher. Back in those times, the temperature was pretty warm. If we go into this period here, now we're looking at about 10 million years to about 70 million years in this period here. And you can see that, well, they started out warm, but they started cooling. So during this time, they started coming down. So by the time we got to about 7, 8 million years ago, the temperatures were down pretty close to where we are today. And then they went down even more, and these are ice ages here, and we're looking back about 500,000 years. We're within 1 million years now. About 500,000, you can see ice ages, and then over here, it's the end of the last glacial period, which is when Cape Cod was formed, and from here, this 2 on across is what you saw on the previous chart. Okay, so we've kind of expanded it so we can fit the whole picture on here. Now, to put this into perspective, I want to add some important things to it. It was back here about 20 million years ago that we saw the first reptiles. Our history shows the first reptiles. We think the first life on Earth started about 3.8 billion years ago. It took a long time to get to the point where they were crawling around. First reptiles, about 200 million years ago. About 100 million years ago, we had the first mammals. Dinosaurs became extinct about 50 million years ago, and it's during this last really hot period when that happened. The first great apes, about 10 million years ago. And by this time, the temperatures are getting down pretty close to what we know. Genus Homo, that we belong to, is here about 3 million years ago, and now we're talking about a temperature that's probably cooler than where we are today. And finally, Homo sapiens, our species, somewhere around 350,000 years ago. And if we look across here, maybe a couple times for short periods, the temperatures have been warmer than they are today. But we can't say that human beings, Homo sapiens, this has happened before, it's not a big deal. What we're seeing now is probably about as hot as it's been during our existence as a species. And we're going up from there. So we're really entering new territory. This is not like, oh, this has happened before, it's not a big deal. This is new territory for our species. So the Earth isn't exactly warming at the same rate everywhere. It's not like, okay, 1.1 degree, and we're getting 1.1 degree everywhere, so it's not a big deal. Actually, it varies depending on where you are, and there's kind of 3 takeaways from this chart. This shows what's happened since the beginning of the Industrial Revolution. The first thing is the oceans mostly are warming at the surface slower than the land is at the surface. Now, one of the reasons for that is the oceans are absorbing a lot of heat, but it's going down into the ocean, not at the surface. The second thing is there's one little spot out here, and it's about the only spot where the things are cooling. And that has to do with the flows in the ocean and melting of ice on the ice cap in Greenland. Okay. That's why that's there. But that's the only place where we can say, well, this is not balancing at all. There's one little spot where it's cooling, everything's warming. And the other thing is the Arctic is warming much faster than everything else. And the reason that is because there's what we call a positive feedback mechanism. The Arctic is covered with ice. It floats on water. The ice has snow on it. The snow reflects most of the sun away. Well, when you start warming that and start melting it, you replace very reflective snow with seawater. And as it starts to go back, you've got more energy going into the seawater, so you're getting more energy, so that melts more snow and more ice. And so that pushes it back farther. Now you've got more ocean to absorb the water. That's called a positive feedback mechanism, and that's why that's happening up there. This is the same picture, except they've kind of taken an average for the Earth. And so you can see the areas that are slower than the global average and are faster than the global average. And the reason I put this picture up here is I want to show this area. This is a little fuzzy and hard to see. But you folks are right about here. And what you can see is the ocean off your area here is actually warming faster than the land. And that's a little unusual. But that has implications for this area. The ocean is actually warming a little bit faster. We're going to come back to that and talk about what that means. Now I want to step aside from the science for a little bit and talk about policy and politics. And this helps us understand where 1.5 came from. You hear this a lot. What does that mean? Well, and where did it come from? Why did we say that? So back in 1988, we were talking about climate change, and the UN decided we probably ought to take a look at this because it has global implications on the countries that we represent. So they formed something called the Intergovernmental Panel on Climate Change, IPCC. It's a science group. And they told them, go out and assess where we are with climate. And they did. And in 1990, they published what was called the first assessment. And we look back and call it the first assessment. There have been 6 so far. So they do this over and over again. That assessment, if you look at it compared to what we have today, was not real firm about what was going on. This appears to be happening, and and so on. The scientists don't like to say things unless they really know. And we weren't very far into the science at that point. But it was enough that the UN decided, well, we need to do something about this. Well, you don't put scientists in charge of that kind of thing. You need a policy group to do that. So they formed the UN Framework Convention on Climate Change. And it went into effect in 1994. Well, in 1995, the IPCC came out with their second assessment. And it was a little bit more firm about what was happening. But interestingly enough, one of the things they said is, as scientists, to set a quantitative global temperature change limit, we need to state where we want to stop the warming. And that gives us something to base our policies on in terms of what we're going to do. But these guys were scientists. They were just saying we need to do this. They were not in a position to do it. And the political side of the house kicked the can down the road for 20 years. 20 years later, the 21st Conference of Parties, COP21, you've always heard about the Paris Conference. Contrary to something that's been said here recently, the Paris Conference accomplished a great deal. But one of the things they did, for one thing, they got commitments from the countries. The first time they really got commitments from the countries to actually take policy changes to address climate change. And I'll mention that again later. But one of the things they did was they agreed at that conference that we need to cap warming at less than 2 degrees. And they actually said well under 2 degrees. Now that's not exactly quantitative, but it's something that gives you an idea of what you want. But they also told the IPCC, go out and run a scientific investigation for us of what's the difference in terms of climate impacts between 1.5 and 2 degrees, and what's the difference in how we get there? How hard is it? How much more difficult is 1.5 than 2? And so they went off and did this work, and they came out with a report. This is the IPCC, the science group, came out with a report in 2018. And they had a number of conclusions, and this is a very complex business, so I'm not going to go into a huge amount of detail, but one of the conclusions was we look at numbers on a global scale, 1.1 now, 1.5, 2, and so on, and it's hard to get your arms around that. But what they said is if you look at it regionally, there are big differences in regional weather and regional change between 1.5 and 2. So it really does make a difference on a regional basis. One of the things they said was they expect 10 million fewer people to be impacted by sea level rise if we stop it at 1.5 versus 2. They looked at ecosystems and biodiversity and things like that and came up with a very interesting conclusion. This is a little complicated to understand, but they looked at over 100,000 species of plants and animals. And what they discovered was that the number of species losing half their range, you know, species live over a range of land, and some of the species were going to lose some of that range. The number losing over half their range doubled for plants and vertebrates. And for insects, it tripled. And you may not think that's important, but insects play an extraordinarily important role in our ecosystems. And the number that we're going to lose over half the range tripled between 1.5 and 2 degrees. They also talked about increases in ocean temperature and acidity. Both of those go up significantly. They didn't say anything unless if it wasn't significant, they didn't talk about it. Oxygen level in the ocean decreases. That's a bad thing for things living in the ocean. And then all the things we see of health, livelihood, and so on, all that kind of stuff. Everything gets more difficult at 2 than it is at 1.5. And they also said it's easier to adapt to 1.5 than 2, which is kind of a no-brainer, but they did make that statement. I want to go back to the climate change and the science part now and talk a little bit about climate change impacts. And I've just picked out some of them because they're kind of interesting and to look at. This isn't all of them. Some of them are global, some of them are regional, and some of them have effects that spread about happening in one place but spread around the globe. And one of those is this one here. This is the Greenland ice cap. This is the mass change on the Greenland ice cap. And this really is a measure of how much of it is melting. We know it's melting. We can actually determine how much it's melting because we have a satellite that measures gravity. And gravity is based on mass of objects. Okay, so if the mass changes, if the gravity changes, then the mass changes. So you can relate those two. So the satellite goes over and over and over Greenland and it measures the gravity. And it started, this is 2002. When we first put this satellite up, this is 2022, here, there's a little hole right there because the first satellite wore out and we didn't get the second one up in time. So we lost some data in that little hole right there in 2017. The numbers aren't real important here. It's gigatons and so on. But what we're really seeing is the change in gigatons, in mass, and it keeps going down. And this is the melting effect. the mass keeps going down. And almost every year, it's zigzag because it goes down in the summer, then it goes up the next winter when you get more snow. And then it starts to melt again and it goes back down. So that's why you got this zigzag pattern. But almost every year, the amount you have in the winter, when you have the maximum amount, is less than last year. And almost every year, the amount you have in the summer, when you've melted it off, is less than you had last summer. So there's a continual decrease of this thing over time. Why is this important? This spreads around the world. This effect spreads around the world because it raises the sea level. This is sitting on land. It's not like you know the ice cap sitting on land. So when the water runs off, it runs into the sea and it raises sea level. The sea ice in the Arctic is changing dramatically. And we talked about earlier, I talked about how the sea ice was changing and that the Arctic is warming faster and the positive. Well, this shows that from 78 to about 2022, we have about a 60% decrease in the summer in the amount of area covered by ice in the Arctic. It's a little messy, you know, year to year it goes around, but if you draw a line down it and average it, that's what it looks like. In the winter it's dropping too, but there are geographical reasons why it doesn't change so much in the winter, and I don't have time to get into that, but it's a significant drop in the sea ice. The ocean heat content is going up, and that's something you may not understand very well, but we talk about the extra heat that's coming into the Earth atmosphere system. Almost all of it's going into the ocean. And the heat content is going up. And it raises the temperature, but the ocean can absorb a lot of heat without having a huge temperature increase. And all this blue, from here all down to this deep blue here, that represents heat absorbed by the ocean. The yellow here is heat absorbed by the land. The gray here is heat absorbed by glaciers and ice caps. This little maroon thing down here in the bottom is heat absorbed by the atmosphere. Now imagine, if you will, if the ocean wasn't out there absorbing heat, we wouldn't be here. But it does. And just to give you an idea, I've blown up this little part down here, and this little bit down here is the amount absorbed by the atmosphere. So most of the heat that's coming into the Earth atmosphere system is going into the oceans. One of the things that does is as the seawater warms up, it expands. What does expanding seawater do? It causes sea level rise. It can't go down. It's got to go someplace. It goes up. It causes sea level to rise. And of course, then we can put all this together and say, okay, this is the sea level rise we've seen, starting with 0, and this is in millimeters. Let's change it to inches so you can make more sense out of it. This is sea level rise you can see since 1900. Lots of interesting things here. During the 50s, 60s, and 70s, we built a lot of dams, and we dammed up rivers, and the water didn't flow very much down to the ocean anymore. We held a lot of that back to charge the reservoirs behind the dams. When those all got full, then it started up again. But we actually had a flat spot there in sea level rise we created by building dams. And you can see this is tidal gauges here and satellite data going up here. And the satellite data is a lot smoother. We have much better data we can use from satellites. Originally, it was glaciers in the Greenland Sea and the Greenland ice melting. Now we've added to that Arctic melting, Antarctic melting, and thermal expansion of the ocean, which has become a factor lately because of the heat going into the ocean. So sea level rise is a concern on its own, but the pace is about tripled. For most of the last century, it was about a half an inch per decade. So what's that telling you? About 5 inches over the century. It's now more than 3 times that rate. Just recently, more than 3 times that rate. So it's become quite a concern. The result is about 7 inches in the last 100 years. That's the global average. And Woods Hole, it's been about 10 to 12 inches over the last 100 years. So you're seeing more here. And it varies depending on where you are. The red arrows on this are greater than 8, and a lot of them are a lot greater than 8, but along the Gulf Coast. And some areas on the Atlantic seaboard have seen more, a little bit lower up in this area here, and there are areas where it's actually falling. So it's not the same everywhere. And to look at sea level rise, NOAA has a sea level rise viewer where you can go in and look at a map and say, okay, what happens if you put this much in this much? So I did that for a couple things here just for the fun of it, and learned a lot about Cape Cod. You guys, you think you're low-lying. You're not as low-lying as you think you are. I was asking Tom, and he's about 50 feet. Well, 50 feet sea level rise isn't going to happen anytime soon. But we can expect maybe by the end of this century, 2 feet or so. And so this is the sea level rise viewer that NOAA has, and you can go in and run scenarios on this. This is today. And I said, okay, what happens if we get 2 feet of sea level rise, say the end of the century? And I was surprised that it's not terribly dramatic. You see some areas, all this light blue you see around the edges is areas that disappear under the water, but there's not a whole lot of them, to be honest. There's also a sea level rise viewer that the Cape Cod Commission has. And what they've done is, the best I can figure out, is taken NOAA's and then superimposed on it interesting things and important things on Cape Cod. And these red dots here are important facilities that are going to be impacted by 2 feet of sea level rise. And this is, you recognize this area, you know where we are here. And it's interesting that all these, except one, are either landings, boat landings, or and that makes sense. I mean, if you're going to land or launch a boat, it's got to be at sea level. You've got to put it there. So those are going to be impacted. The one that shows up on here that doesn't fall into that category is this one right down here, and that's the Rotary. You probably know this. There's a group already looking at roads around here that are affected by sea level rise, and this is probably one of the more important ones. I'm sorry. The light green is low-lying areas that become saltwater marshes and stuff like that aren't before. Low-lying areas that are susceptible to that. You have to understand that this is based on an average. This does not have things, and I'll come back to this, but it doesn't have things like storm surge, and it doesn't have coastal erosion in it. That kind of thing is just how it's. Here's the land, and you raise 2 feet. And look like then, and so it doesn't have all those other impacts that are going to make it worse. One of the things is that the continental shelf has been warming fast. The water in the continental shelf has been warming very fast, and this is line here, and again you have all these, a lot of scatter in the data, but if you draw a line to it, that line right there is the continental shelf, the northeast continental shelf. This is the global number down here. So it's 5 to 10 times as fast as the ocean, the global ocean is warming. And that has some implications. You can see this is a summer line and a winter line, and you're getting a little bit more change in the summer than in the winter, but it's warming in the winter too. I don't think I'm telling you a whole lot here. You've probably heard a lot of this before. Well, one of the things that happens when you change the temperature of the water is that the things that live out there have to do something. Something happens to them if they're susceptible. Now, some things just aren't susceptible, but in this case, what they plotted here is where this is the latitude, and it's kind of the center of where these animals are. And you can see that the black sea bass has migrated north over time. This is 1970, and this is today over here. You probably all know this. The lobster has migrated north, the American lobster. The interesting thing is the Atlantic cod has not. It's stayed the same area, but there's another issue there. This has to do with migration and productivity of species. So the top here is the lobsters, and this is on the Gulf of Maine and Georges Bank. You can see the number of lobsters. This is biomass, but essentially how many lobsters you have goes up. This is the New England, southern New England area, and it peaked out in the 1990s, and it's gone down since then, and down very low at this point. The black sea bass it not only migrated north, but it helped it out because it's more productive than it was. There's something about, now could be something else that caused that, but the black sea bass has migrated north and become more productive. But the interesting thing is, remember, the Gulf of Maine cod did not migrate. It's almost disappeared. And I don't know, I don't know enough about it to know, is that because they couldn't migrate or what the issue was. But this gives you an idea of the kind of impacts you can have because things are, the water's warming out there. And it changes the ecosystem for what lives out there. Rain and drought. Typically, we have more rainfall in extreme rain events. And we've had numerous studies to show this. The rainfall events that are very, very heavy, you get more rain out of than we used to. And somebody did a study recently where they looked at the extreme 1% of storms, the heaviest rainfall storms, the extreme 1%, how much rain occurred in that and how did that change? And they looked at back in the 50s and now and discovered that all across the United States, all the regions of the United States, the percentage of rain you got in extreme storms went up. And this region here was the highest. You get about half again as much rain out of the most heavy storms you have than we got 50, 60 years ago. You may know this. I mean, things, but one of the things I know is the gutters. I had gutters put on my house about 5, 6, 7 years ago. Those gutters are a whole lot bigger than the ones I had on the house when I grew up and the ones they took off the house that were put on 30 years ago. The problem we have with that is we're doing a better job of getting it off the roofs and into the gutters and into the storm sewer, but it's a lot harder to make the storm sewers bigger so they can handle all that extra water. We're having trouble doing that. We've also know that periods of heavy rain and periods of drought have increased. And they're kind of opposite of each other. But we learned this from that satellite I was telling you about that takes gravity, because what they actually look at is groundwater. Groundwater has mass. It changes the gravity of an area. You don't notice it walking around, but this satellite is very sensitive and it picks it up. And it has figured out that they looked at 1,000 events in the last 20 years and figured out that they are much more extreme. The droughts are more extreme than they used to be because it's drier. There's less groundwater, and the heavy rainfalls are more extreme because the amount of groundwater goes up. And so they've seen this change in how extreme these events are by looking at the groundwater. And they've also correlated that it tends to happen more where temperatures are higher. So the concern is now we have rising temperatures, this is going to get worse. We don't know that, it's just a concern. But that's a serious problem. For the coastal environment, we talk about increasing water temperature. We've talked about that. Saltwater intrusion. It changes ecosystems along the shoreline. You may have a freshwater ecosystem that suddenly becomes a saltwater ecosystem, or a mixture that becomes pure saltwater. And also, you get saltwater intrusion into freshwater wells. And this is a serious problem, and particularly in an area like this where everybody's on wells. You can have salt water as it rises get into those wells. Florida is having a real problem with this right now. Reef bleaching, that's a nice word for killing the reefs. They turn white because everything dies. That has happened down in the Caribbean. Mostly you hear about it in Australia, but it's happened here. Increasing erosion in storms, and I mentioned this earlier. It's not just the sea level rise. It's when that rises, it changes the dynamics of what's going on the shore and increases the erosion you have on the shoreline. That's especially going to be a problem with the occasional storm, tropical storm that comes up here, or the much more regular, nor'easter that you've been through here. Working conditions, if you're in an area, if this doesn't apply to everybody, you're in an area where it's already hot. They're already having to deal with this in the South of how do you protect people from extreme heat as they're working outside. Urban areas are a problem because they hold heat, and so they get hotter and they don't cool off at night. And if you don't have air conditioning, there's a physiological problem of your body doesn't recover if it doesn't get cooled off at night. And disease, a lot of the vectors for diseases are insects, and they thrive in warmer temperatures. So we worry about diseases spreading more than they do now because the vectors can live. And I'm not going to go through these, but there are a million other things that, I shouldn't say that, a whole lot of other things that are happening, that severe storms, I talked about that, but ecosystem disruptions, most of the things I've talked about. Agriculture, we really rely on that, and it's being impacted. And then there's the political, economic things happening as people can't live someplace and they have to go someplace else and nobody wants them, and there's just all kinds of things like that. So those are real problems. So how do we respond to this? What do we do? Well, remember the 1.5 degrees. How do we get to 1.5 degrees from where we are today at 1.1 degrees? It sounds like it's easy. It's not. These lines here are, this is CO2 emissions, how much we put out into the air. And these lines here are pathways to get us to 1.5. If we just said back in 2000 that, oh, we got a problem, let's hit this thing, and we smooth the curve out and start down, we could decrease a little bit, and we'd have, we'd make it, it wouldn't be so hard. But the longer we wait, the steeper the curve gets. This black line here happens to be if we'd started in 2019. We have to make very rapid decreases. Now we're over here someplace and it's going down. And exactly what year it is depends on who you talk to. But what we're really talking about, we need to reduce greenhouse gases is to go to net zero by 2025, 2026, something like that. Very, very quickly. We're probably not going to do this. 2 degrees is a little bit easier. The curve is at least, might be able to accomplish it. Realistic projections, national pledges that were made at the Glasgow Summit in 2021. The nations came in and said, here's what we're going to do to try to fix this problem. They think that would probably get us down to 1.8, which is under 2. That's probably a good thing if we could do that. But that's not what we're doing. Those are pledges for the future. What we're doing now, current policies, is 2.8 degrees, which is almost twice the 1.5, which is the goal. So this is not good. So what can we do about it? Well, I tell everybody become a voting and vocal advocate for climate change. And I'm not sure this is necessarily a problem here, but the difficulty we have with voting is that people care about it, but it's not very high on their list of how they choose who they vote for. You can imagine in 2016, a Pew Research poll said 80% of Americans believe that climate change is happening. What did we do in 2016? We elected a president who said climate change is a hoax. And 80% of the people said they believed climate change was happening. Obviously, they weren't factoring climate change into how they voted. And in 2022, Yale survey came out and they said, well, we need to, this is, entire United States, we need to regulate CO2 as a pollutant. 72% said we need to regulate CO2. Strict limits on CO2, limits of coal-powered power plants, 66. Provide tax rebates for energy vehicles and solar panels, 77%. Schools should teach warming, 77%. Congress should do more to address warming, 61%. What did we do in 2022? We elected a Congress. There's no way they're going to pass any legislation there that's going to address this issue. And the reason, that's why I say it's important to get climate change, push it up on your priorities for who you vote for. It's sitting down at 4 or 5. Yeah, it's important to me, but it's not that important. These are more important, and it's got to get up there. Personally, reduce consumption of meat. If you're not vegetarian, you don't go vegetarian, just don't eat as much meat. If you're going to eat meat, stay away from beef and lamb. Those are the ones that put the most methane into the air. Reduce, reuse, recycle. I want to emphasize recycle is the last resort. You start by reducing. You reuse what you have if you can't reduce. And the last resort is you recycle it. But don't think because you recycle that you're doing your part to address climate change. Go hybrid or electric if you can with your vehicle. Walk, bike, carpool, anything you can to get out of your car. Use less hot water. There are lots of opportunities to do this if you think about it. Just go through a day at home and think about what you're doing with hot water because you have to heat that water. Lower your thermostat. You've all heard that. Change your light bulbs. If you're still using incandescents, get rid of them. Turn off electronics. How many times have you been in somebody's home and the TV's going in that room over there and there's nobody in that room? Avoid cryptocurrency. Some of you know this. Most of you probably don't. Cryptocurrency uses an enormous amount of energy. I won't go into detail, just trust me. An enormous amount of energy to run what's called blockchain, which is the process for cryptocurrency. You do not want to get involved in that. There are other reasons why you probably should stay out of it too. Encourage others to do these things, okay? Encourage others to do these things. Important. It's okay to be a pain in the butt for climate action, folks. You can do that. So, I would like to thank you all for your attention, and I've really enjoyed this opportunity, and I'd like to answer some questions if I can. Okay.
So our friends here are going to be collecting any questions, and while they do that, I have a question already from one of our audience members. Is there a tipping point in temperature rise that takes us beyond the point of no return?
The best answer I can give to that is probably not from a temperature perspective. We don't know for sure, but we have other tipping points. The temperature is kind of the baseline on this thing. Temperature causes other problems, and that's what worries us about tipping points. And one of the big tipping points people talk about is what's going on in the Antarctic. And the concern there is there's a tipping point there. It's hard to relate to temperature. It's probably out there someplace, but we may have already passed it. But what's happening is we're getting to the point where we're melting away the part of the ice that holds the glaciers in place in Antarctica, and an enormous amount of the fresh water in this Earth is in those glaciers in Antarctica. And the concern is if we get to the point, those glaciers could start moving, and the process will not stop until we've pretty much gotten all that off of there. And we're looking at 200 feet of sea level rise if that happens. Now, that's not going to happen this century. It's a long process. But that's the kind of tipping point we're talking about. What I can tell you is we've really had trouble identifying definitive tipping points, and to say, well, we know if this happens, we're done. You know, it's going to keep going. So I would say we don't know whether or not there's a temperature tipping point. That's simply, we may have tipping points in other areas that affect other things, but I'd have to say I can't say that, you know, 2.5 or 2.8 or something like that is a tipping point that means from that point on we're just going to keep getting warmer. There's been some optimism recently that we used to look at scenarios that took us out to 6, 7, 8 degrees, and we're becoming a little bit more comfortable now that we think we're on a track to at least avoid those extreme scenarios. Like I showed you, if we keep doing what we're doing today, we're still looking at about 3. But we do think that we're probably on a track to avoid the extreme, and that suggests that there's no tipping point in that we just go off the scale. Do you want to ask a question?
What do you think the extreme climate, the temperature change in New England and the Northeast, how extreme it is, that we're sort of sticking out?
You are not, you're sticking out, but in terms of the land mass here, your temperature change is average. The water temperature change is not average, okay? But the land temperature change here is going up. It's not that it's not going up, but you guys are not extreme. Actually, the real extreme is in the Arctic. And there are some other areas that are extreme. But here, it's going up, but it's not extreme, you know, just in terms of your thermometer out on the land. Yep.
So there's 2 questions that are very similar, and I kind of asked them together. Cape Cod has been actually spared by storms in the past few years. What might be the reason why we have been spared for so long? And also, how much do you think we will experience in the future extreme weather with more global warming? More hurricanes and so on and so forth? What's in store for the Cape? And
I don't know how long you've been spared. You said several years? Yeah. Well, I don't want to scare anybody, and I'm not putting out a forecast here, but we have just been through what's referred to as a triple dip La Nina. And you're familiar with El Nino? That's the story. Well, the opposite of an El Nino is La Nina. And that actually affects what happens to the weather around the entire world, which is hard to imagine. And I've been doing meteorology now for 50 years, and it's just, to me, when I first started out, if somebody had told me that something happening out here, back in those days off the coast of Peru was going to cause, worldwide and even across the South Pacific, which is amazing, but it does. We have just been through 3 consecutive years of La Nina. It's happened before, but it doesn't happen very often. The forecast now, and what we're looking is we are going into an El Nino year this year, and it's probably going to be a very robust El Nino. Very robust El Nino. And which means we'll see the global temperature go up significantly from when it's been the last few years and so on. But it impacts a lot of places. And it may kick something over that'll cause things here. That's the first way I'll answer that, is we have these global things going on that actually sort of affect what you have. The other thing is, regardless of those, storms come and go. And there's a certain probability, and it may be improbable that you go 4 or 5 years without a big storm. But that doesn't mean something has necessarily changed. We expect this year we'll probably have fewer hurricanes than normal, but that doesn't mean that you won't have one wander up this direction. There's just so many imponderables that go into this, but I would not attribute the lack of storms here to a climate change thing, and I wouldn't expect that's something that's going to continue to happen. We expect that in general, storms are going to be more robust. We may not have more, but they're going to tend to be stronger. That's what we know. We look at tropical storms, hurricanes, and so on. We can't say that we're going to have more of them, but what we are very comfortable with is they're going to be stronger than they have been in the past. And that may be true for nor'easters and other types of storms too. So what's happened, count your blessings and get ready for the next one.
Why is the Gulf of Maine the fastest warming body of water on Earth?
That's because of the Gulf Stream has changed its course a little bit. And that all has to do with general circulation of the atmosphere in the oceans. The oceans actually have these slow currents that flow generally across the top of the ocean and across the bottom of the ocean, and they connect all. You don't think about that. They connect all around the globe. The major connection point is around Antarctica, because you can go all the way around the globe at Antarctica, but then they come up, and in the Atlantic, there's a current that comes up along the bottom of the ocean slowly, and it gets up to Greenland area, and it comes up, and then it works its way back down. And there's all these eddies and little things going on in that. And the Gulf Stream, which actually moves north, is part of that overall process. That process is being disrupted. We know that's called the Atlantic Meridional Overturning Current, AOMC. And we know that is slowing down a little bit. And it's got a lot of people concerned, because it's part of our overall climate that we're used to. And when you start having something that's that big and that consistent, to start changing, we're concerned about what are the impacts on the air climate associated with that. But that's part of it, is that the AOMC is slowing down some, and they think they attribute some of the changes that are going on with the Gulf Stream to what's going on with the AOMC. But the Gulf Stream has changed its course in how it extends and how it moves. And that's really what we're using to blame the warming of the Gulf of Maine.
What caused the Earth to move out of the ice ages into an optimum period?
That's a great question. I have slides on that. Don't have time to show you. There's something that climate change deniers have said, well, we don't have a global warming problem. We have a global wobbling problem, because the globe wobbles. and that's causing climate change. And it does. Actually, there are three things in our orbit in the Earth that cause long-term climate change, and it really has to do with ice ages and that type of thing. The first one is the axis of the Earth, and what it rotates on moves back and forth. Most of us don't know that. We don't see it. It moves so slowly. It takes about 40,000 years to go through a cycle, but it's tipping like this. And that affects how the sun hits and the angle the sun hits where you are. That's the first thing. There are two other things. One of them is the orbit we go around the sun goes back and forth from being an ellipse and a circle. And it actually does that on two cycles. One of them is about 100,000 years long, and one of them is about 400,000 years long. But it does that cycle. And it makes a difference because when it's in a circle, we're always the same distance from the sun as we go around. But when it's in an ellipse, there are times when we're closer and times when we're farther away. And that really affects how much energy we get from the sun. The third effect is a little bit more complicated. It has to do with that tilt I was talking about and that orbit. And that tilt isn't always associated with orbit the same way. Sometimes the tilt is lined up at the part that's extended, and it tilts towards the sun. But sometimes the tilt is on the near part, and it tilts towards the sun. And so the axis of the tilt, it is not aligned with it when you're farther away. It's a hard thing to understand, but that works on about a 22,000-year cycle, that going back and forth. And that is the one, that and the 400,000 one are the ones that most affect ice ages. And there was a gentleman named Milankovitch who studied this. He was doing other things and was captured by the Germans in the 30s, and they said, you can't do that other stuff, you go do something else. So he decided, oh, I'm going to study the tilt of the Earth and all that kind of stuff, and ice ages. And he came up with this theory that this is what causes ice ages. And he was ignored for a long time. And when we started looking at climate change and wanting to look back in geologic history and understand what went on, they dug his work out again and pretty much validated that what he did was correct. So we know that that's what does it. And that's why when people say, well, it's the wobble of the Earth that's causing, climate change. Well, it does cause climate change, but it doesn't cause it on the time scale that we're dealing with now. It's a long time scale. Yes, ma'am. Milankovitch.
How do you talk to skeptics? Are certain facts more persuasive, or are facts not the way to go?
Boy, that's a good question. If I had a good answer to that, I'd be doing a lot more good in this world. I think you have to gauge who you're talking to and what they're saying. And there are people that you're not going to reach no matter what. And there's no point in spending a lot of time talking with them. But there are people who are a true skeptic. The difference between a denier and a skeptic. A true skeptic, you can talk about your experience with things that have changed and what you experienced when you were younger and what you're experiencing now. And you can talk about what you've learned from things like this and other things. You can talk about those things to a skeptic and try to explain it. And that's probably a useful thing to do. But I would start with a personal experience. So that you can say, well, here's what I've experienced. Not what I read in the book, or not, here's what I've experienced. And here you can do that. You can say, well, we were down at Woods Hole, and the sea levels come up a foot in 100 years. Something's happening there. And I know there are people who've, old guys, I shouldn't say that, I'm an old guy, worked in shipbuilding along the East Coast, who said in 1990, I can tell you the sea level's rising because they worked in the same facility for 50 years, and they saw the sea level rise. So those kinds of things are, I think, much more convincing than well, I read in such and such.
I think we'll actually get through these. Why does the ocean absorb more heat?
Why does the ocean? That's a really good question. It has to do with the chemical properties of water. For one thing, we all know that if you take a bowl full of water and a bowl full of air and you weigh them, the water is going to weigh a lot more. It's a lot denser. Okay? And so that alone allows it to absorb more heat because there's just more mass there to absorb it. But it's the chemical properties of water that allow that, and the difference is dramatic in terms of that. And water is really, really important to what we do here, not just in the normal life cycle, but in the way the climate works. I talked about how evaporating water gets water off the heat off the earth, and that's a very real thing. That has to do with that whole process has to do with why we have thunderstorms and why we have hurricanes and so on. That process I described there. As you go up and the air cools, the air can't hold as much water, so it has to give off the water. It has to evaporate that water out because it can't hold as much. What happens when it evaporates the water out? It releases the heat. That makes it rise faster. That's why we have thunderstorms. It's a process, a self-fulfilling, positive feedback process that forms that. So water is really important to us. The fact that when water freezes, it expands rather than contracts is a good thing because now it's floating on top of the water down below. If water didn't do that, it would freeze from the bottom up, and our lakes would never thaw. They'd become just all ice. So water has all these interesting characteristics that actually make things work here. We've all evolved, the entire Earth has evolved to live with the way water works. So,
Here's a question, a little different. I'm not quite sure I understand it. Referring to electric cars, the electricity production of charging your car it's causing CO2.
well, it depends, yeah.
So that's kind of a...
Yeah. Let me address that, because you hear that a lot. I have an electric car. One of the ways around that problem is that I have solar panels on the roof of my house. And so I charge my car from the sun. But it's true that if you don't have that facility, that you're buying electricity from somebody. Now, if you're in Texas and you're charging your car there, something like 38% of the electricity in Texas is generated from wind turbines. So it's not all coming from fossil fuels. In other areas, actually where I live, most electricity is generated from fossil fuels. We have I'm from the outside of DC in Maryland. Most of our electricity is generated through fossil fuels. Not much coal, but fossil fuels. But studies have shown that even charging that way, you put less CO2 in the atmosphere driving electric than you do driving a standard vehicle. And it just has to do with the way the efficiencies of how they generate electricity and how it's passed and how the car uses it and so on work. And I didn't bring that slide with me, but they've done studies of all different kinds of cars, and you can go into whatever part of the country you're in and whatever kind of car you're driving and see what it is. But typically, almost all vehicles in all areas around the country are at least somewhat more efficient in terms of CO2 release in the atmosphere than an internal combustion engine. But it's better if you charge it. There's better ways to do it.
Okay, a couple more questions. Yeah. Is the thawing permafrost above the Arctic Circle factored into the methane total?
Say that again.
The thawing permafrost above the Arctic Circle, is that factored into the methane?
Yes, it is.
Total, it
Yeah,
is?
yes, it is.
Okay.
Yes, it is. And it's a hard thing to do, but we are paying a lot of attention to the tundra region in the northern region and trying to understand. It's a very important area for climate, trying to understand that. And we've discovered all kinds of really interesting and sort of fun things, but we talked about ecosystem changes and so on. There's an area in the tundra up north in North America, and I can't remember whether this is in Alaska or Canada or both, but they discovered an area where it was mostly just tundra, and they discovered all these ponds suddenly, within a 10-year period. All these ponds up there. What on earth is this about? Why are we? And they thought it was melting. Well, what they discovered was, as things warmed, trees started to grow up there. It wasn't just the tundra. Trees started to grow. Guess what came with the trees? Beavers. And they built dams and dammed up the creeks. And now you got all these lakes up there, and they're actually beaver ponds up there. So we're watching, finding all kinds of interesting things, but we're watching that carefully. And yes, we are looking at that. And that is a concern of just how much are we going to have released from what's been buried down in there for all this time. And it's a serious concern, yeah.
So there's one more question, and
Yeah.
I think you talked about it earlier, but I think we all could use the repetition on it. Why exactly is the Arctic warming much faster than the Antarctic?
Well, that question is a little bit different. I didn't address why the Arctic is warming faster than the Antarctic.
True.
I addressed why the Arctic was warming faster than the rest of the world. The Antarctic is warming. We have a couple problems with the Antarctic. One of them is we don't understand it as well. We don't have the presence there, and we have land masses that push up against the Arctic, and people live there, and so we really kind of understand what's going on up there. There are no land masses that push down against the Antarctic. That's number one. Number two, it's a different environment. It's land with ice on top of it. The Arctic is ice floating on water. Mm-hmm. There's no land up there. And so that complicates things too. And it's just been hard to get a handle on that. The Arctic has these currents flowing all the way around it. The Antarctic has these currents flowing all the way around it. The Arctic doesn't have that at all. It's got land mostly around it. That changes it. One of the really interesting things in the Antarctic is we've seen this significant decrease in sea ice in the Arctic. And we understand that, but in the Antarctic, it's been different. We've had trouble getting a handle on it, and the reason is the sea ice in the Arctic only expands relatively little because it hits land. And once it hits land, it's run out of place to expand. And most of the Arctic is surrounded by landmass. The Antarctic has no landmass at all surrounding it. The change in sea ice in the Arctic is enormous. It expands by about 15 times what it is in the summer, southern hemisphere summer, about 15 times, and goes away to almost nothing. And then it grows way back, and it's like 15 times that. When you have that kind of variation, from a statistical point of view, it's hard to establish significance. If the data is small and you get a handle on it, that's one thing. But when the data is noisy and real different, it's very difficult to establish significance of change. So when we say, yeah, it's less this year than last year, but you've got this enormous thing, well, does that make any difference? So it's taken us about 20 years of monitoring that to get enough data and become comfortable that we can say it really is changing. But we're getting a point now where we know that the amount of sea ice in the Antarctic is changing. It is going down. But it's just hard to deal with that way. You remember I talked about the fact that the sea ice coverage changes a lot in the summer in the Arctic, but not much in the winter, a little bit, but not much. And the reason it doesn't change much is it doesn't have any room to grow. The only places where it can change are certain areas, and it goes down, but it can melt away completely, but it only can grow so far, and that's why. So the Arctic is warming. We're comfortable that the Arctic is warming. It's a different type of climate, a different type of issue. When ice melts in the Arctic, it's floating on the water. It has no impact at all on sea level. None at all. When ice melts in the Antarctic, it's running into the ocean and raising the sea level. So it's a whole different ball game down there. And to be honest, we're still trying to get our arms around it.
Change the salinity as well?
Excuse me?
Does it affect the salinity as well?
It does.
All right, it's 7:30. I guess we have to wrap up. Let's thank Jeff for an amazing presentation.
Thank you all very much. I've really enjoyed this. I appreciate the opportunity, and keep working.